Title: Time Complexity, the Science of Scalability. Today we are going to discuss one of the most fundamental concepts in computer science, time complexity. Whenever we write a program, our first objective is to ensure that it produces the correct result. However, correctness alone is not enough. An algorithm must also be efficient. As the amount of data increases, an inefficient algorithm may become impractical, regardless of how powerful the computer is. Time complexity is a mathematical tool that helps us predict how the running time of an algorithm changes as the input size grows. Rather than measuring execution time in seconds or milliseconds, we analyze how the number of operations increases with larger inputs. This allows software engineers to compare algorithms even before implementation. Whether we are designing search engines, machine learning systems, databases, or operating systems, understanding time complexity enables us to build software that scales efficiently. Throughout this presentation, we will explore the principles of time complexity, understand asymptotic analysis, compare different growth rates, and see why choosing the right algorithm often matters far more than upgrading hardware. Title: The Hidden Cost of Code. At first glance, it may seem that buying a faster computer can solve performance problems. However, this is a common misconception. The first point on this slide reminds us that hardware speed cannot compensate for poor algorithm design. A slow algorithm may appear acceptable for small datasets, but as the input size grows, its execution time increases dramatically. Even the most advanced hardware cannot overcome an inefficient algorithm. The second point introduces the concept of abstract counting. Instead of measuring time with a stopwatch, which varies depending on the processor, operating system, and programming language, we count the number of fundamental operations such as comparisons, assignments, or arithmetic calculations. The third point explains the core mission of time complexity. Our goal is not to measure the current execution time, but to predict how an algorithm will behave in the future as data grows. Therefore, time complexity serves as a blueprint for scalability, helping us design software that remains efficient even when handling millions or billions of data elements. Title: Measuring the Invisible. Now let us understand the key components involved in analyzing time complexity. The first concept is input size, represented by the variable n. The value of n depends on the problem. It may represent the number of elements in an array, the number of records in a database, the number of nodes in a graph, or the number of users accessing a system. The second concept is basic operations. Instead of counting every instruction executed by the CPU, we focus on the operations that dominate the running time. Examples include comparisons, arithmetic operations, assignments, and function calls. The third concept is language and hardware independence. Whether an algorithm is implemented in Python, Java, or C++, its mathematical time complexity remains the same. Similarly, running the algorithm on different computers does not change its theoretical complexity. This makes time complexity a universal method for evaluating algorithms. Title: The Growth Rate Spectrum. This slide introduces the most common categories of time complexity. The first is constant time, represented as O(1). Here, execution time remains the same regardless of input size. Accessing an element in an array using its index is a classic example. Next is logarithmic time, written as O log n. Binary search is the best-known example. At each step, the search space is divided into two equal parts, allowing extremely fast searching even in very large datasets. The third category is linear time, represented as O(n). Linear search examines every element until the target is found. As the number of elements doubles, the execution time also roughly doubles. Finally, we have quadratic time, represented as O(n superscript 2). Quadratic complexity usually appears in algorithms with nested loops, such as bubble sort. When the input size becomes large, the number of operations increases dramatically, making such algorithms inefficient. Understanding these growth rates allows us to choose algorithms that remain practical as data scales. Title: The Worst-Case Reality. When analyzing algorithms, computer scientists usually focus on the worst-case scenario. Why is the worst case so important? In real-world applications, we cannot predict the exact input our program will receive. A user might upload an extremely large dataset, or a malicious attacker might intentionally provide inputs that maximize execution time. Therefore, the worst-case complexity represents a guarantee that the algorithm will never perform worse than the specified bound. The slide also contrasts three types of analysis. The best case describes the most favorable situation. The average case estimates typical behavior based on assumptions about the input. The worst case provides the strongest guarantee because it prepares us for the most demanding conditions. For software used in banking, healthcare, cybersecurity, and cloud computing, worst-case analysis is particularly important because reliability cannot depend on favorable inputs. Title: The Asymptotic Toolkit. This slide introduces the three fundamental asymptotic notations used in algorithm analysis. The first notation is big O, written as O(g)(n). Big O represents the upper bound of an algorithm's running time. It tells us the maximum amount of work an algorithm may perform. The second notation is big omega, written as omega(g)(n). Big omega defines the lower bound, indicating the minimum amount of work required. The third notation is big theta, represented as theta(g)(n). Big theta combines both upper and lower bounds, providing the most precise description of an algorithm's growth rate. Together, these three notations allow us to mathematically describe algorithm performance under different conditions. Title: Case Study: The Search Showdown. Let us compare to searching algorithms using an example involving 1 billion records. The first approach is linear search. Linear search checks every element one by one until the target is found. In the worst case, it may need to examine all 1 billion elements. Now consider binary search. Binary search repeatedly divides the search space into two equal parts. Instead of 1 billion comparisons, binary search requires only about 30 comparisons. This example demonstrates an important principle. The right algorithm is not simply a small optimization, it fundamentally transforms the performance of the entire system. This is why algorithm selection often has a greater impact than hardware improvements. Title: Simplifying the Math. When expressing time complexity, we simplify mathematical expressions by focusing only on the dominant term. There are three important rules. First, we keep the dominant term. For example, in the expression n superscript 2 plus n, the quadratic term grows much faster than the linear term, so we keep only n superscript 2. Second, we remove lower order terms because their contribution becomes insignificant for very large values of n. Third, we ignore constant coefficients. For example, 4n and n both have linear growth, so both are simply written as O(n). These simplifications allow us to focus on the overall growth behavior rather than insignificant implementation details. This approach forms the foundation of a synthetic analysis. Title: Exponential Explosions. This slide introduces exponential complexity, represented as O2. Exponential algorithms become impractical very quickly because each additional input element doubles the amount of work required. For relatively small values of n, execution time may already become impossible to manage. Many famous computational problems belong to this category. Examples include the traveling salesman problem, subset sum problem, and Boolean satisfiability problem. These belong to the class known as NP problems, for which no polynomial time solution is currently known. This leads to one of the greatest unsolved questions in computer science, the P versus NP problem. If someone discovers a polynomial time solution for NP-complete problems, it would revolutionize computing and mathematics. Because of its significance, solving this problem carries a $1 million Millennium Prize. Title: Designing for the Future. As we conclude, let us summarize the key lessons from today's discussion. Whenever we develop software, we should first analyze different algorithmic approaches before writing code. Choosing an efficient algorithm early can save enormous computational resources later. Scalability should always be considered a core software requirement. Applications that handle 1,000 users today may need to support 1 million users tomorrow. Finally, remember that investing in better hardware only provides temporary improvements. Improving the algorithm itself produces permanent performance gains. Therefore, successful software engineers optimize the algorithm first and hardware second. In conclusion, time complexity is much more than a theoretical concept. It is an essential tool that enables us to design scalable, efficient, and future-ready software systems.